Welcome back to the deep dive. If you are tuning in today, I need you to maybe put your phone on, do not disturb, clear your desk, and maybe even grab a notebook.
Yeah, this isn't going to be a casual listen.
No, not at all. Today isn't for when you're commuting or, doing the dishes. We are shifting gears into a really high-intensity revision mode.
We're treating this session as well, a complete top-down architectural review of the material.
Exactly. To everyone listening, we are addressing you today as learners because the primary goal here is precision. It's about retention and ultimately exam-ready recall.
That's the mission.
We are tackling the massive multi-domain topic of military technology, specifically focusing on naval and air power.
But we aren't just listing equipment today.
No.
We are taking the machine apart to see how it works. We're stripping away the fluff to focus entirely on the mechanics and the doctrine.
And we're not just going to memorize names of ships or planes. We're going to understand the ecosystem they inhabit.
Right. The goal, the mission for this session, is to make sure that by the end, you have a complete mental map of all this material.
A mental map, I like that.
We're going to traverse the naval domain, looking at why ships are classified the way they are. Then we'll dive underwater to look at the chemistry of propulsion.
And after that?
Then we move to the air domain to break down the physics of stealth. And finally, we ascend to the space domain.
To look at surveillance and what our source material calls domain awareness.
Exactly.
It sounds like a complete vertical slice of the armed forces' technological capabilities. I mean, from the crush depth of a submarine all the way to the vacuum of geosynchronous orbit.
It is. And to keep this organized, to make that mental map possible, we are breaking this down into 4 distinct conceptual layers.
Okay, and why is that structure so important?
Structure is absolutely critical for retention. It's simple, really. If you can't visualize where the information lives, you won't remember it during an exam. It'll just be a jumble of facts.
So what are the layers?
Okay, so layer 1 will be the naval ecosystem, the hardware floating on the water.
The ships themselves.
Right. Layer 2 is advanced subsurface technology. We'll get into the weeds on Project 75I and air-independent propulsion.
AIP, right.
Layer 3 takes us up to the sky for aerial dominance stealth, the AMCA, and countermeasures.
And the final layer.
And layer 4 covers high-altitude operations and space surveillance.
Okay, learners, let's get started. Let's initiate layer 1. Diverse vessels of the naval force. Now, often when people talk about the Navy, they throw around terms like frigate, destroyer, cruiser, almost interchangeably.
You hear it all the time.
It feels like random nomenclature. But in a technical context, these distinctions matter, well, enormously. They aren't just about size, are they? They're about mission and reach.
That's the key. You have to view the modern Navy not as a random collection of boats, but as a sophisticated, interdependent ecosystem.
But an ecosystem.
Yes. Think of it like a biological food chain or even a corporate hierarchy. And at the very top of that hierarchy, we have the strategic assets.
Your heavy hitters.
The heavy hitters, exactly. And the primary asset here is, of course, the aircraft carrier.
The floating air base.
Precisely. But let's define it by its capability, because that's what really matters. An aircraft carrier isn't just a big ship. It is a platform defined by its ability to carry somewhere between, say, 30 to 80 aircraft.
With full runways.
Full runways for takeoffs and landings, catapults, arresting gear, the whole system. These vessels are the command center of a task force.
And their power source gives them incredible range.
Incredible. Whether they are powered by nuclear reactors, which gives them essentially unlimited range and endurance, or more conventional gas turbines, their one mission is global power projection.
Okay, power projection is a term we hear a lot in these texts. What does that actually mean in this context? Let's break that down for the learners.
It means you can park a piece of your sovereign territory off the coast of another nation, anywhere in the world, and operate a sovereign airfield from it.
So you don't need permission from anyone.
You don't need a friendly neighboring country to let you use their airport. You bring the airport with you. That capability, just its presence, changes the entire geopolitical calculus of a region immediately. It shifts the center of gravity.
Okay, and paired with carriers in this heavy hitter category are submarines, but they operate on a totally different philosophy.
A completely opposite philosophy. If the carrier is the loud, visible show of force, the big stick that everyone can see, the submarine is the ultimate stealth asset.
A silent service.
Exactly. Their primary capabilities are obviously underwater travel, carrying a very serious array of heavy weapons, and crucially, long-endurance patrols.
And how long are we talking?
A single submarine can stay on patrol, underwater, for up to 6 months.
6 months, that's incredible. The psychological pressure on the crew must be immense, but let's just stick to the tactical pressure it creates.
The tactical pressure is all about denial. Their mission profile is aggressive. Attacking enemy ships, launching missiles from a concealed position, they are the denial force.
What do you mean by denial force?
A carrier controls the sea. A submarine denies the enemy the use of the sea. An enemy commander can't be sure where it is, so every one of his ships is always at risk. It's a huge psychological weapon.
So if the carrier is the command center and the submarine is the silent hunter, that makes them both incredibly high-value targets.
The highest.
Yeah.
The enemy wants to sink them first.
So what protects them? This must bring us to the next level down, the surface combatants.
The bodyguards, we call this the protective ring. And we start with the guided missile cruisers.
Cruiser. It sounds almost antiquated, like a term from World War II.
The name is old, but the role has evolved dramatically. Today, a cruiser's primary role is defense, specifically area air defense.
So they're looking up, not out.
Mostly up. They're designed to create a massive bubble of safety around the carrier. They are packed with advanced systems. The text mentions things like the NAG, BrahMos, and Barak 8.
And their job is purely defensive.
Their primary job is to shoot down anything, incoming missiles, enemy jets, drones, that tries to touch those high-value assets. They are the shield bearers of the fleet.
Okay, moving down the line from cruisers, we have destroyers. Now these seem to be the real workhorses of the fleet.
They are the versatile powerhouses. A cruiser is a specialist. A destroyer is a generalist, but a very powerful one.
How so?
A destroyer is designed for land attack capabilities as well as multi-domain defense. That means it's built to fight threats from the air, from the surface, and from underwater, all at the same time.
And to really understand the technology here, the text gives us a specific example to look at, the INS Imphal.
Yes, the INS Naval is a perfect case study.
The text mentions it has enhanced stealth features resulting in a reduced radar cross-section, or RCS. Let's pause there for a second. How do you make a 7,000-ton ship stealthy? I mean, it's enormous. It's a huge block of steel in the ocean.
It's all about geometry. It's physics. A traditional ship has vertical walls, right? And lots of 90-degree corners. Think about railings, antennas, deck houses. In physics, a 90-degree corner is known as a corner reflector. It has a special property. It bounces radar waves directly back to the source that sent them.
Like shining a flashlight into a corner of a mirrored room.
Exactly. It comes right back at you. So to a radar, a normal ship with all those corners just lights up like a Christmas tree.
So the INS Imphal just eliminates those corners.
It eliminates them or hides them. The INS Imphal uses angled superstructures. The walls of the ship slope inwards, or they're faceted like a diamond.
So the radar waves hit a sloped surface.
But when the enemy radar energy hits these sloped surfaces, it's reflected away, upwards into the sky or downwards into the water. The key is, it doesn't go back to the enemy's receiver.
So on their screen.
To the enemy radar, this massive destroyer might look like a small fishing boat, or maybe just random sea clutter. That is RCS reduction.
That's fascinating. The text also notes the INS Imphal is equipped to fight under NBC conditions, nuclear, biological, and chemical warfare.
It is.
That sounds terrifying, but what does that actually mean for the engineering of the ship? What's happening inside?
It refers to the citadel concept. So imagine the ship is sailing through a radioactive fallout cloud or a chemical weapon attack. The first thing that happens is the ship seals itself hermetically. All doors, all vents, slam shut.
But a seal can't be perfect. There are always going to be tiny leaks.
You're right. And that's why a seal isn't enough. The ship's ventilation system, which is now a closed loop, creates overpressure.
Overpressure.
They pump highly filtered, clean air into the sealed-off living and working spaces of the ship. They pump it in until the internal air pressure is higher than the outside atmospheric pressure.
Ah, so if there is a tiny leak...
Clean air blows out. Toxic air can never get in. It's a simple, brilliant concept.
And this allows the crew to operate without wearing full hazmat suits inside the ship.
Exactly. Even while the world outside is toxic, it speaks to the incredibly high-intensity environments these ships are expected to not just survive, but fight in.
That is incredible engineering. Okay, so moving on from destroyers, we have frigates. Now, historically, I think of these as smaller escort ships.
Historically, yes, that's exactly what they were. Frigates were the eyes and ears of the fleet, often used for anti-submarine work or protecting slow merchant convoys from U-boats.
But that's changed.
It has, and here's a critical trend for our learners to grasp. The distinction between destroyers and frigates is blurring.
How so? What's driving that change?
Two things: weapon miniaturization and increased lethality. Decades ago, you needed a massive ship to carry a massive, powerful missile. The electronics, the fuel, it was all huge.
But not anymore.
Not anymore. Today, modern frigates, like the INS Tuchel or the Chivalric class, which are mentioned in the text, possess hugely increased offensive capabilities.
Yet they're not just defensive escorts anymore.
Far from it. They can strike land targets hundreds of miles away. They carry heavy anti-ship missiles. They're becoming, for all intents and purposes, pocket destroyers.
Okay, that covers the combatants, the fighters. But a navy also needs to operate near the coast and, support landings on a hostile shore. This brings us to a whole other class of vessels, the specialized and support vessels.
Right. And for operations near the coast, in what's called the littoral zone, we have the littoral combat ships, or LCS.
What defines an LCS versus, say, a frigate? They seem similar in size.
It's about modularity and depth. An LCS is designed for shallow waters where a big destroyer might run aground. But the key operational feature is its modularity.
What do you mean by modularity?
You can swap out entire equipment packages, like shipping containers. One mission, it's equipped for mine hunting. They unplug that module and plug in a new one for special ops support or maybe anti-submarine reconnaissance.
And they can do this quickly.
The design goal is to be reconfigured overnight. And crucially, they are designed with a huge amount of automation to allow for much smaller crews, which lowers the long-term operating costs.
And when we need to move troops from the sea to the land?
That is the amphibious group. And it's really a triad of logistical movement. You have three types of ships working together.
Okay, what's the first?
First, you have the amphibious assault ships. These look a lot like mini aircraft carriers, but instead of jets, they feature large helicopter decks for airlifting troops and equipment inland.
The second part of the triad.
Second, you have the amphibious transport docks. These are interesting. They have a well deck in the back, which is a big internal bay that can be flooded with seawater.
So it opens up to the sea.
It opens up, and they can release landing craft directly from inside the ship for a beach assault.
And the third?
And third, you have the dock landing ships. Their main focus is on carrying the landing craft themselves and also providing critical maintenance and refueling capabilities for those smaller craft.
It's a complete delivery system for an army from the sea right onto the beach.
It is.
And strictly on logistics, we can't forget the support ships.
The unsung heroes. The fleet literally cannot function without them. They're the logistical backbone.
They're the floating logistics.
Exactly. Tankers carrying fuel, ships carrying food, ammunition, repair parts, everything a fleet needs to stay at sea for months. And a critical subset here is the hospital ship.
And these aren't just floating ambulances with a doctor on board.
No. These are floating hospitals. I mean, full-scale medical facilities with multiple operating rooms, x-ray labs, intensive care units, burn wards. The works.
So they're used in war, but also for other missions.
Yes. They're also major diplomatic assets. When a natural disaster like a tsunami or an earthquake hits a coastal nation, sending a hospital ship is one of the most powerful forms of aid you can provide.
Okay, before we move to layer 2, I really want to visualize this. Expert, can you walk the learners through a mental map of this naval hierarchy?
Certainly. This is a great way to lock in the information. So learners, if you can, close your eyes for a second. Visualize a target with 3 concentric circles.
Okay, turret.
In the bullseye, the very center circle, that's where you put your strategic assets. The carrier in the submarine. They are the queens on the chessboard, the most important pieces.
Got it. The bullseye.
Now, in the middle ring surrounding them, that's where your bodyguards live. The destroyers, the cruisers, and the modern powerful frigates. They are creating that protective shield we talked about.
Right, the protective ring.
In the outer wing, operating on the edges and near the coasts, you have your specialized vessels, the LCS and the amphibious group.
Okay, so center, middle, outer. Where does the support ships fit?
The support ships are the lines connecting all 3 rings. Think of them like supply lines on a map, providing the fuel, the food, the sustainability for the entire system.
Excellent. Okay, everyone, lock that image in your mind. Now, let's transition. Let's move to layer 2. Advanced subsurface technology.
We're going underwater.
We are. And we're focusing on Project 75 and this key concept of air-independent propulsion, or AIP.
This is a critical technological shift for the armed forces. Project 75I envisions the indigenous construction of 6 Calvary-class diesel-electric attack submarines.
And the I is important here.
The I stands for India, and the mandate here is heavy on indigenization.
Okay, what are the numbers on that? What's the target?
The mandate laid out in the source is very specific. The first submarine must have a minimum of 45% indigenous content.
And that number goes up.
It does. By the time the sixth submarine is built, that must rise to 60%.
Why is this percentage so important? Is it just, a matter of national pride?
No, it's about strategic resilience. It's a hard lesson learned over many decades. The text points to a specific economic focus. Boosting MSME development, that's micro, small, and medium enterprises, to manufacture the spares and systems.
So it's about the supply chain.
It's entirely about the supply chain.
Yeah.
Imagine you are in a major conflict. Your most advanced submarine needs a specific critical valve that is only made in, say, Germany or Russia, and your supply lines are cut.
Your submarine is dead in the water.
It becomes a very expensive, useless steel tube. But if that valve is made by a small factory in Poon, you have supply chain security. Indigenization is a defense strategy, not just an economic one.
That's a great point. Okay, now let's get to the technical core. The text highlights a massive difference between conventional diesel-electric submarines and those equipped with AIP. Let's break down the limitation of the conventional sub first.
Okay, so let's look at the mechanics. A conventional submarine is essentially an electric vehicle. Underwater, it runs silently on massive batteries.
Right. But batteries don't last forever.
Exactly. When the batteries get low, it needs to recharge them. And it uses a diesel generator to do that.
And diesel engines need air. Lots of it.
They do. They need to breathe atmospheric oxygen. So, to run those generators, a conventional sub must come up to snorkel depth, which is just below the surface, or even the surface completely.
And how often does it have to do that?
Roughly every 48 hours. It has to stick a mast out of the water to suck in air and vent exhaust.
And that surfacing, that snorkel, is the moment of maximum vulnerability.
It's the matchstick in the woods analogy.
Yeah.
You're in a dark forest, completely hidden. The second you light a single match, your position is revealed instantly to everyone for miles around.
Because that mast can be detected.
The snorkel mast can be picked up by radar. The heat from the diesel exhaust can be seen by thermal sensors. The noise of the engines can be heard by sonar. It breaks the stealth. For those few hours of charging, the hunter becomes the hunted.
So how does air-independent propulsion AIP solve this fundamental problem?
AIP allows a non-nuclear submarine to generate electricity without accessing atmospheric oxygen.
It brings its own air, so to speak.
It brings its own oxidizer on board. It provides a supplementary power source that can trickle charge the batteries while the sub is still deep underwater, completely concealed.
What does that do to the performance? What's the practical difference?
The difference is night and day. It's a game changer. Instead of surfacing every 48 hours, an AIP-equipped submarine can extend its submerged endurance up to 2 weeks.
From 2 days to 2 weeks, that's a massive tactical advantage.
It is. Persistence equals stealth. The less you have to surface, the safer you are.
Now, the text lists several ways to achieve AIP. It's not just one technology. Project 75I has a specific standard, but let's review the variations so the learners understand the whole landscape.
Okay, so there are 4 main types of AIP variations mentioned in the source material.
What's the first?
First, you have open cycle systems. These often use stored hydrogen peroxide, which decomposes to create steam and drive a turbine. It's effective, but the turbines are mechanical and make noise.
Okay, what's next?
Second, closed cycle diesel. This is a very complex system that basically runs a diesel engine underwater by recycling its own exhaust gas and mixing it with stored liquid oxygen and argon.
Sounds complicated.
It is. Third, a similar concept, closed-cycle steam. This uses ethanol and oxygen combustion to drive a steam turbine. Again, you have a turbine, which means noise.
And the fourth type?
The fourth is the Stirling cycle. This is a type of external combustion heat engine. It burns liquid oxygen and diesel fuel to create heat, which then drives the engine to charge the batteries.
But Project 75I focuses on a very specific type, correct? It's not one of those 4.
Correct. The standard specified for Project 75I is fuel cell technology.
Why fuel cell? Why is that the chosen standard? What makes it better than, say, the Stirling cycle?
One word: silence. A Stirling engine has pistons. It has moving parts. Moving parts create vibration, and in the ocean, vibration is noise. Noise is death for a submarine.
And a fuel cell has no moving parts.
None to speak of. A fuel cell is an electrochemical device. It converts chemical energy from a fuel like hydrogen and an oxidizer like oxygen directly into electricity. There's no combustion. There are no pistons.
What are the byproducts?
It creates electricity, heat, and pure water. That's it.
So it's the quietest possible option.
It is the gold standard for stealth in a non-nuclear submarine. Now, it requires storing highly pure hydrogen and oxygen on board, which is a significant engineering challenge, but the tactical payoff of being nearly silent for 2 weeks straight is considered worth it.
One final clarification here, expert. Is nuclear power considered a form of AIP?
That's a great question, and it's a point of frequent confusion. Technically, yes, nuclear power is air-independent. A nuclear reactor certainly doesn't need oxygen to function.
But it's not categorized that way.
Exactly. In military categorization, we treat nuclear propulsion as a separate class entirely. When we say AIP in this doctrinal context, we are specifically referring to these technologies that boost the performance of conventional non-nuclear vessels.
That's very clear. Okay, let's ascend. Let's move to layer 3. Aerial dominance. This is a big one. It covers stealth, the AMCA project, and countermeasures.
Right.
Let's start with the fundamental principles, the physics of stealth. I think a lot of people think stealth just means invisible, like in a movie.
It's a very common misconception. Stealth isn't invisibility, it's delayed detection. The goal is to shrink the distance at which an enemy can detect and track you.
And it's not just about radar.
No, it's about reducing your total signature. And there isn't just one signature. There are at least 5 domains to worry about. Radar, of course, but also infrared, which is heat, visible light, radio frequency, or RF emissions, and audio.
The text mentions passive design considerations. How do engineers achieve this physically on the aircraft itself?
They fundamentally alter the shape of the aircraft. For instance, instead of a single vertical tail fin, they might use split rudders or canted vertical stabilizers angled outwards. This helps deflect radar waves away from the source.
What about the heat signature?
That's where thrust management comes in. They design the engine exhausts to mix cool bypass air with the hot engine exhaust core. This lowers the overall temperature, making it harder for infrared sensors to lock on.
And then there's the big one, internal storage.
Crucial. Absolutely crucial.
Why is carrying weapons internally so important?
Think about a normal fighter jet. It's covered in things hanging under its wings. Missiles, bombs, fuel tanks. All of these are jagged, complex metal shapes.
They're all corner reflectors.
Exactly. To a radar, they shine like Christmas lights. A stealth aircraft must carry all its weapons and most of its fuel inside its belly, inside an internal weapons bay. The skin of the aircraft must remain as smooth as possible.
But these designs, these strange shapes, they come with significant trade-offs. You can't just make a plane smooth and angled and expect it to fly perfectly.
No, you can't. The primary limitation is aerodynamic instability. These stealth shapes like flying wings or faceted diamonds are often inherently unstable. They want to flip over in the air.
So how do they fly?
They require incredibly complex fly-by-wire computer systems, making thousands of micro-adjustments to the control surfaces every single second just to keep the plane flying straight. The pilot isn't really flying the plane. They're telling the computer where they want to go, and the computer's figuring out how to do it without crashing.
Then there is the thermal issue you mentioned.
Yes, even with thrust management. Supersonic flight creates immense friction with the air. It heats the skin of the aircraft to very high temperatures. This skin heating increases the infrared footprint, making the plane visible to heat sensors, which can counteract some of the radar stealth.
And the payload issue, you can't carry as much.
Right. Because everything has to fit inside the fuselage, you simply have less room. You can't carry as much weaponry or fuel as a conventional bomb truck aircraft that has pylons all over its wings. It's a trade-off between lethality and survivability.
This brings us to the indigenous answer to these challenges. The AMCA project.
The Advanced Medium Combat Aircraft. This is the ambitious mission to develop an indigenous fifth-generation multi-role stealth fighter designed to eventually replace the aging Su-30 MKI fleet.
And it's designed to be a generational leap.
A significant one. The text notes the Mark I variant will feature 5.5 generation technology, with the Mark II planned to integrate 6th generation upgrades later on.
Let's visualize the specific design features mentioned in the text for the learners. What about the wings?
The design calls for shoulder-mounted, diamond-shaped trapezoidal wings. This shape is specifically chosen for something called planform alignment.
What's that?
It means making sure that as many of the leading and trailing edges of the aircraft, the wings, the tail, the control surfaces, all align along a few common angles. This scatters the reflected radar energy into very specific, narrow spikes, rather than all over the place, making the aircraft much harder to detect from most angles.
Okay, and the air intakes. The text calls them S-shaped or serpentine ducts. Why an S shape?
This is one of the most critical and difficult to engineer stealth features. If you look straight into the front of a normal jet engine, you see the fan blades of the compressor.
Right, the big spinning fan.
That spinning metal fan is a massive radar reflector. It's like putting a disco ball right in the heart of your aircraft. It will light up any radar that looks at it.
So the S-duct hides the fan blades.
It hides them completely. An S-shaped duct curves the airflow. If you look straight into the intake, you can't actually see the engine face. The radar waves go in, they hit the curved walls of the duct, which are coated in special radar-absorbing material, and they bounce around to get absorbed until they run out of energy. They never hit the fan blades. It blocks the line of sight for the radar.
The text also makes a point of mentioning supercruise. What is that?
Supercruise is a big deal for stealth. Most jets need to use afterburners to go supersonic. An afterburner dumps raw fuel directly into the hot exhaust stream.
Creating a massive flame.
A massive plume of fire and heat. It's like a rocket engine. It gives you a huge boost in speed, but every infrared sensor in the sky can see you. You're broadcasting your position.
And supercruise avoids that.
Yes. Supercruise is the ability to sustain supersonic flight without using afterburners. The AMCA's engines are designed to be powerful enough to fly faster than sound in what's called military power, or dry thrust. It lets you be fast and cool, maintaining your stealth.
Okay, moving from the aircraft itself to its defense systems. We need to talk about expendable active decoys, or EADs. The source describes them as electronic bodyguards,
And that's a good way to think of them. The key word here is active.
as opposed to passive countermeasures like chaff.
Exactly. Standard chaff is passive. It's just clouds of tiny metal foil strips. It's like throwing glitter in the air to try and confuse a camera. An EAD is an intelligent robot. It is a small, sophisticated jamming system that gets launched from a standard chaff and flare dispenser.
And it actively transmits signal.
And it actively transmits powerful jamming signals designed to fool an incoming missile.
The mechanism here relies on a concept called angular separation. This sounds like a physics term. Can you explain that concept for the learners?
I can. So imagine a radar-guided missile is tracking your aircraft. Its seeker head is locked on to you. You release an EAD. The decoy powers up in milliseconds and starts screaming electronic noise that's designed to mimic your plane's radar signature, but much louder and more attractive to the missile. The missile seeker says, "Aha! That's my real target over there."
So it starts to turn towards the decoy.
It does. But here's the trick. The EAD has a small parachute or some other method to create drag.
A parachute? Why? To slow it down.
Precisely. Your plane is flying at Mach 1. The decoy deploys its little chute and slows down dramatically. In seconds, the physical distance between you and the decoy grows very, very rapidly.
And that's the angular separation.
That's the angular separation. From the missile's point of view, its target has suddenly moved and is slowing down. It continues to follow the louder target, the decoy, and turns away from you. This creates what the pilots call a large miss distance. The missile goes through the decoy and you escape.
So the whole concept of operations, the Kona PS, is basically detect, eject, radiate, and decelerate.
That's a perfect summary. The radar warning receiver on the plane detects the threat, the decoy is ejected, it radiates the jamming signal to seduce the missile, and it decelerates to physically pull the missile's flight path away from your own. It effectively shouts, "I'm right here, come get me," while the actual plane speeds away.
Fascinating. It's all about buying you those few critical seconds of life. Okay, let's transition. Let's move to layer 4. High-altitude operations and space surveillance. And we're starting with a rotorcraft built to solve a very specific problem, the HAL Prochend, or LCH.
The Prachand's origin story is tied directly to the Kargil War. It's a direct result of the lessons learned there.
What was the lesson?
During that conflict, the armed forces realized a painful truth. They lacked a suitable attack helicopter that could operate effectively in the extreme high altitudes of the Himalayas. Standard, heavy gunships from other countries just couldn't generate the lift needed in the thin air. The Prachand is the specific answer to that problem.
What is the defining metric here? What makes it so special?
Altitude. Its primary capability, the thing that makes it unique, is that it is the only attack helicopter in its weight class in the world that is capable of taking off and landing at an altitude of 5,000 meters.
5,000 meters, that's 16,400 feet.
With a full combat load of fuel and weapons.
That is incredibly thin air. Physically, that means less oxygen for the engine to burn and less air for the rotor blades to push against to create lift. How does it survive in that environment tactically, not just physically?
Tactically, its design focuses on low visibility. It has a very narrow fuselage. The two pilots sit in tandem, one behind the other, not side by side.
To reduce its frontal cross-section.
Exactly, making it a smaller target head-on. It uses digital camouflage patterns designed for mountain terrain. And to counter heat-seeking missiles, which are the main threat in those environments, it uses large IR suppressors on the engine exhausts to cool and mix the hot gases, hiding that heat signature from enemy sensors.
Okay, let's talk about its teeth, the avionics and weaponry.
It utilizes a modern glass cockpit with an integrated avionics and display system, or IADs. But the real game changer for this kind of warfare is the helmet-mounted sight, the HMS.
How does that work?
It directly connects the pilot's eyes to the chin-mounted turret gun. In older helicopters, to shoot something, you had to turn the whole helicopter to face it. You had to fly the gun. It was cumbersome.
But not with an HMS.
With an HMS, the pilot simply looks at the target. Sensors in the cockpit track his helmet's exact position and orientation. The 20-millimeter turret gun under the nose swivels instantly and automatically to match his gaze.
He looks, he shoots.
He looks, he shoots. It is a massive force multiplier in the winding, narrow valleys of the mountains, where maneuvering the whole aircraft is difficult and dangerous.
And what about the weapons payload?
It carries that 20-millimeter turret gun. It can carry 70-millimeter rockets and, of course, air-to-air missiles for self-defense. But for its primary ground attack role, it carries the Drivastra air-to-ground missiles.
Why is the Drivastra specifically highlighted in the source material?
Because of its target profile. It's specifically noted for its ability to destroy hardened shelters. In mountain warfare, the enemy isn't standing out in the open. They are dug into fortified bunkers in the rock. You need a missile capable of penetrating concrete and rock before it explodes. That is the Drivastra's specialized role.
Okay. Finally, we move to the ultimate high ground, space. The text outlines the space-based surveillance project, and specifically SBS-3.
SBS-3 represents a massive scaling up of our space-based surveillance capabilities. It's a program to launch 52 AI-powered spy satellites over a period of 5 years.
And this is to complement existing assets.
Yes, it builds on and enhances the network we already have with satellites like RESAT, Cartosat, and the GSAT 7 series.
The text is very clear in categorizing these satellites by their sensor type. Learners pay close attention to these distinctions because they define what we can actually see from space.
Right. There are 5 main classifications in the text. First, missile early warning. These use powerful infrared sensors to detect the massive heat bloom of a ballistic missile launch. They give you the first critical seconds of warning that an attack is underway.
Second,
Nuclear detection. These are designed to specifically spot the unique double flash signature of a nuclear detonation, both in the atmosphere and in space.
third is electronic.
Yes, electronic reconnaissance, or SIGINT, for signals intelligence. These satellites don't see, they listen. They intercept radio waves, radar signals, and other electronic chatter from an adversary.
And fourth is what we normally think of as a spy satellite.
Right. Optical imaging. These are basically your giant high-powered telephoto cameras in orbit. They provide incredible detail, but they have a fundamental weakness. They're fair-weather friends. They can't see through clouds. They can't see at night.
And the fifth and final type solves that weakness.
It does. The 5th type is radar imaging, using synthetic aperture radar, or SAR.
How does SAR differ from a camera? What's the mechanism?
A camera is passive. It just collects reflected light. SAR is active. It's like a bat. It shoots a beam of radio waves down at the Earth and then listens for the reflection, the echo.
And radio waves go through clouds.
Radio waves go right through clouds, and since it provides its own light, it works just as well in pitch blackness as it does in broad daylight. Its critical advantage is 24/7 all-weather monitoring. It creates a map based on the texture and density and shape of objects on the ground, not on light.
Now there is one final program mentioned that shifts the perspective entirely, the Silent Barker program.
This is a crucial distinction for learners to understand. SBS-3 and all the sensors we just discussed look down at the Earth. Silent Barker looks up and around at space itself. This is what we call space domain awareness.
So it's not watching the ground, it's watching other satellites.
Exactly. Its goal is the custody of space objects. It is specifically designed to detect and track threats to our own high-value assets in geosynchronous orbit, or GEO.
Why the specific focus on GEO? That's 22,000 miles up. It's incredibly far away.
Because that is where this strategic backbone of our entire network lives. Our most important communication satellites, our missile warning satellites, they sit in GEO.
Why there?
Because at that specific altitude, a satellite's orbital period matches the Earth's rotation. To an observer on the ground, it seems to hover over one fixed spot.
So they are stationary relative to the ground.
They are, which is great for communication, but it also makes them predictable stationary targets. And because they are so far away, it's very hard to know if an adversary's satellite is trying to sidle up next to one of yours to disable or damage it.
And that is why silent barker is needed.
That's its entire purpose. It's a neighborhood watch for the most expensive and critical real estate in space. It ensures that if an adversary's vehicle drifts too close to one of our GEO assets, we know about it immediately.
So we have eyes on the ground with SBS-3 and eyes on our assets in the sky with silent barker.
Precisely. It's a dual-layer surveillance architecture, one looking down, one looking up.
Learners, that concludes our 4-layer revision. I know that was incredibly dense. So let's do a rapid chapter-level summary to lock all of this in before we sign off. Expert, can you bring it all together for us?
Let's recap the linkages between the layers. In the naval domain, we saw a complete ecosystem. From the power projection of aircraft carriers protected by the RCS-reduced destroyers like INS Imphal, all the way to the stealth endurance of Project 75 submarines, using quiet fuel cell AIP to stay submerged for 2 weeks.
Okay, the air domain.
In the air domain, we analyzed how stealth is a game of physics. It's about reducing signatures, a principle realized in the AMCA with its S-ducts and planform alignment, and defended by the clever angular separation created by active decoys.
Rotorcraft in space.
In the rotorcraft domain, we saw how the Prechand is a purpose-built solution to a specific physics problem-generating lift at 5,000 meters while carrying bunker-busting Dravostra missiles. And finally, in space, we established that critical distinction between looking down at Earth with SAR and optical sensors like an SBS-3 and looking up to protect our geosynchronous assets with silent barker.
So the connecting thread here, the theme that runs through everything, is that modern warfare is no longer just about who has the biggest gun or the fastest plane.
Correct. It's about these other qualities. It is about persistence, the ability to stay underwater for 2 weeks. It is about invisibility, whether through radar stealth or IR suppression. And it's about situational awareness, seeing through clouds with SAR from space, or targeting an enemy simply by looking at him with a helmet-mounted sight.
A final thought for you to take away. We discussed how modern frigates are blurring the line with destroyers by becoming more offensive, more multi-role. I want you to consider how that trend of multi-role capability appears in every single layer we discussed today, from the Prechand helicopter to the modular littoral combat ship. Specialization is good, but versatility seems to be the future.
Indeed. In a rapidly changing and unpredictable battlefield, flexibility is the ultimate survivability trait.
Learners, take a moment to visualize those diagrams we discussed. The concentric naval circles, the S-shaped intake of the AMCA, and the parachute of the decoy pulling a missile away. Visualization is one of the most powerful aids to retention. Excellent work today. We will see you on the next deep dive.
Stay curious and keep learning.
Signing off.